All right, folks. Welcome to week 3. This is going to be the start of our introduction to some data structure stuff. Over the course of this semester, so you'll be receiving evaluations for me as a teacher. When I see that and have more information, I'll let you know. But nonetheless, let's start up with questions from last week. Does anyone have any questions about the course content outline, topics that we went over last week? What's data structure? Why are we using algorithms? Why do we study order of growth analysis? What is big O and things like that? You can also ask your questions in Zoom chat if you like, or unmute yourself anytime, okay? You don't need to raise your hand. So I'll be monitoring your chat activities in case you have questions. All right, any questions about your reading? Chapter 1 through 4. Sorry, 1.4 through 1.6. All right, any questions about your homework? Well, I guess there's no homework, but quizzes. All right, just be mindful of the quiz due date. There's really no extension for quizzes. They're pretty simple, quick, in 30 minutes, and it could be done. But this week, you'll be getting homework assignment. So let me just quickly go over it. Your responsibility for this week is 1 quiz, 1 homework assignment, and they're both due a week plus a couple days, and 21st. Okay, so it's not due tomorrow, but next Sunday. If you have questions about any of these, you can come back and ask me on Saturdays. For a Java quiz or for any quizzes in general, once you take it, you really don't take another attempt. Okay, so you'll be asking question after you take the quiz, I guess. But for homework assignments, if you haven't done it, you can post the questions in. But for quizzes, if this relates to a particular questions you have on a problem in the quiz, I may not be able to give you a solution, but I'll guide you in the right direction. All right. Otherwise, the office hours stays current if you need help with respect to anything, including Java syntax. Yeah. Cool. Let's quickly look at to date. We're going to go over 2.1, 2, 3, 4, and this is your reading assignment, pretty much from the entire chapter, from beginning to end. Okay, and we're going to look at ADT for stack as the blueprint for building, your house, which is your data structure stack. We're going to look at stack as a collection of elements. We're going to look at how this ADT is constructed in Java and also the specific implementations. There's also the 2 things that we're going to look at per data structure, and that is implementation in arrays and linked lists. You may see array-based stack implementation. We'll see if we can get to linked list-based stack implementation. Otherwise, part of 2.5 continues. I think there's 2.6 there too. But since this is the very first time we are diving into data structure, I want to give you some time to absorb these things, especially get acquainted with the Java interface, polymorphism, and so you can kind of see in generics, see how this works. Okay, and there is a homework assignment that complements this week's. There's also a self-assessment. This is where you'll be asking questions about to kind of assess yourself, your competency level in understanding certain topics. For those topics that you feel most confident about, you should do a 30-second explanation in front of the mirrors or someone else to see if you can memorialize that concept. Okay, and then you get 1 assignment point for doing it. Totally honest system. And if you don't do it, that's okay, but don't say that you did it. That would be fine. You'll be gaining point from other avenues this or vehicles this semester. Okay. All right. In terms of your learning objectives, you're going to learn something about generics. What constitutes a Java interface, polymorphism using generics. You're going to look at the examples in Stack. You're going to look at the benefit for using this abstract data types. And then you're going to see how Stack is constructed on the abstract level, application level, and also implementation details. For sure, we're going to get into the array-based implementation, linked list-based maybe next week, but then you're going to be able to compare once you have both implementation details using arrays and linked lists, the efficacies of using either, and so on and so forth. Okay, we're going to know about stacks properties as well. That will be this week. Any questions so far? Reading objectives. Okay. And if you haven't get or gotten acquainted with the intro Java stuff, please continue to do so this week. All right. You might see, yeah, you will see multiple references here. These are snippets that I picked from some of the intro Java, intro C++. We also have stacks there. These are examples. We'll get into it when we get to the section today. Okay. If we don't get to it, these are references, and I strongly recommend that you go through them. And if you have any questions about the materials here, the video topics, you can ping me directly on Slack. Okay. I mean Slack, not Stack. All right. Cool. Lecture 1 is what was left from last week. I said continue, so if you haven't already, please finish that. In terms of lecture 2, every lecture is downloadable in PDF. This is from your textbook, okay? And this is also the source of truth for which all of my video lectures or macro lectures are based on. All right. Questions so far? No? Oh, yeah, I want to make sure everyone can hear me, right? And the sound volume is okay. Yeah, can you guys acknowledge? Yeah? Okay. Yeah, when I see no, I want to make sure I correct that. All right, cool. All right, I'll be playing some of my lectures from time to time, and that's the YouTube hosted videos. If you have sound issues, can't hear, or there's too much echoing, let me know, right? Because I'm doing this from the classroom via my laptop, so I hope everything is okay. All right, let's move on. Yeah, let's talk about Java interfaces. We went through this briefly last week, and here's more in-depth. It actually goes into your 2.1, the same thing. So yeah, let's play this, and then let's discuss afterwards. Let's talk about abstractions here. Now, again, when we're talking about abstractions in the context of data structure, we're talking about abstract data type. But before we get to it, know that the top two, abstractions and information hiding, in this case, this is also what we call encapsulations. Okay. Now, both of these ideas, right, or concept, abstractions and encapsulations are basically the principles of OOP, object-oriented programming language. Your abstraction is basically a quick summary of what needs to be done, a list of things or function signatures that details the reason, right, why you have to do certain things. But it doesn't have what we call how, right, or how things are implemented. So that's abstractions, and inheritance, is part of that. Information hiding, encapsulation is level of access, right? What, as it connotes to the level of access is in the data. And these data would have some, obviously some objectives. Some data will have access to each other. Some data won't have access to each other. And you may have certain things that can only be assessed, right, as a child, but not other objects and things like that, right? So when you put both of these together in the data field, right, in terms of data, right, we're talking about abstract data type now. This abstract data type is, again, a data type described by, predefined user operations, such as, insert data at the beginning of this array, insert data at the end of the array, right, so on and so forth, without indicating how each operation is implemented, right? So this is what, right, but not how. Right? There's no implementation details. So an ADT can be implemented using different underlying data structure for that matter.
like array, linked list, and things like that. So a programmer does not need to have any knowledge of the underlying implementation to use an ADT. Okay, so anyway, so this is abstraction leading to what this ADT is. So let's just use a couple of concrete examples to illustrate how ADT is implemented in Java, because this is a class, a data structure using Java. Let's move on to the next slide. So ADT perspective of levels, we have application, we have abstract level, we have anything. So we talked about this, right? From the very top level, you have abstraction. This abstraction tells you a list, a list of things that would take place, by this concrete class that implements it. So if this is an ADT for a queue, right? So you got the high level, abstract level details. However, the implementations or the how, right? In this case, how is all inside, the data structure. So data structure has all of the implementations. So this is the ADT perspective of levels. So I don't want you to think too much about this, and there's no need to memorize, these application abstractions. Just get the idea, right? The logical levels and the implementation or concrete level. This being the ADT. This being data structure, okay, which is the implementation details. Okay, so that said, let me clear this and let's move on to the next one. Precondition and postcondition. Okay, just like anything else, when you write a function or when you define an ADT, right, with the specific implementation details, there's a set of preconditions and postcondition. Precondition is the assumption that you have to make in order for this ADT to work, or ADT method to work. Postcondition is the effect or the outcome. When this thing is accomplished, what is the end result? And then you have to make sure that both are specified. And this is the reason why when you're designing an ADT, when you go through an ADT, from the perspective of using a Java interface, for example, you have to specify both the pre and post condition for methods. Okay, so this is just a high-level general things that you have to take care of, but we'll get into specific concrete examples. So this is what you would use in Java, let's say, to create abstraction. So there are two ways. One is you can create abstract methods, you can create abstract class. But we're not dealing with classes here, we're dealing with abstract methods. So what is an abstract method? Abstract method is basically just a method signature with a description of the parameters. There's no implementation details whatsoever. It's basically just an interface, right? So we're talking about Java, right? So in other languages, there are no such thing as an interface, but in Java, there's such thing as an interface. So this is an abstract method inside an interface. Now let's look at the interface and what this interface is in Java. So similar to a Java class, this is just a review, and most of you probably have this already. In Java interfaces is something that you can implement. However, similar to Java classes, where you can have variable declarations and method declarations, you cannot have method implementation. There's no implementation. You can have constants defined, basically a public static finals, right? You can also have declaration of variables, meaning you can declare, integer I equals 2, right? For example, in an interface, but method must be abstract. They're not concrete. There is no implementation details in there. So this means that since there is abstract methods in it, you cannot, and there is no constructors or classes in it. A Java interface cannot be instantiated, right? This is all good because you want this interface to do two things. You want to provide the necessary abstraction and encapsulation. Okay, those abstractions and encapsulations. So we can use an interface to specify the logical levels of ADT. And this is perfect because that's exactly what ADT is. You can have the concrete class to implement the ADT, and that concrete class would just be your implementation details and whichever data structure you want to use. So let's just illustrate how this Java interface works in the context of abstractions and data encapsulations. So we have interface called figure interface. Now, this figure interface cannot be instantiated. However, it could be implemented by concrete classes such as circle and rectangle classes. So both of these classes implements this interfaces in Java. So from a mechanic standpoint, let's look at what this looks like in Java. So if you go to the next page, you will see that the figure interface is simply an abstract. It's a whole bunch of abstract methods. There's an abstract methods here. There's another abstract method. It's just a function signature without any implementation details. There's a constant or variable declarations, but nothing else. So this is not concrete, okay? Cannot be instantiated, okay? So that's by design. Now, a circle class implements this interface, right? And by way of implementing this figure interface means that your concrete class, this is the concrete class, has to implement this methods, right? So what is the first method? Parameter. The second one is area, right? So you have parameters and area. This is not override. This is simply just implementing what didn't, okay, inside the figure interface. So class, circle class did not inherit from a figure interface. Simply just basically take in the figure interface and say, hey, this is abstract. Oops. This is abstract, so I have to implement it. And this one is also abstract, I have to implement it. And this is a constructor. Okay. And this is the protected double radius. This is only the reason why this is protected is because you want this protected variable to be used only by the child of circle. You don't want this to be used by rectangles and other shapes. Okay, so this is a quick illustrations of how interface works and how it relates to the concrete classes, and the fact that concrete classes can only have implementation details, whereas interface does not. Okay, all right. The next one up is the same thing, but figure interface is being implemented by rectangle class. Rectangle class implements figure interface and implements also the two abstract methods sitting inside the interface. By default, your final double PI is also available because this one is the interface and it sits on top of your rectangle class. So your rectangle class actually has access to the final double as well, so on and so forth. And this is protected member variables inside the rectangle class. And rectangle class also has a constructor. Okay, so if we put everything inside a UML, like I said, this is a universal model language. Now, inside this class diagram, so we talked about this, right, in lecture 1, where both circles and rectangles now, they're not inheriting from interface, okay? So if this is, let's say if this is an inheritance, the UML, arrow here would have been solid, okay? But this is not solid, this is dash line, right? Dash means that you're not inheriting it, you're implementing. So this is implement. Okay, and interface. Hence the dash line, right? Otherwise it will be a solid one. So when you see an interface on top, you will see these abstract methods being implemented down below. Okay. In this case, they have to be public. They're basically public. And then the very first one inside the concrete class is the constructor. And a rectangle could have its own member variables, so circle member variables, okay? So that's it. This is the UML diagrams. Let's also quickly just go through the benefit of using interfaces. All right, using interfaces allows us to get a glimpse of the contracts. So if you look at all of the methods out there inside the interfaces, and these are abstract methods, there are documentations about what this variables is supposed to be, what this constant is supposed to be, what this abstraction is supposed to be. So you get a glimpse of basically that whole thing. It's a contract, right? There's no implementation details, but for example, let's say this interface is for describing what a stack is, right? Last in, first out. So you basically get a glimpse of all the contract out there in the abstractions. It's like a Rolodex. or a index or table of content, so to speak, right? Before you dive into the specific chapters, you look at table of content. So this is table of content, right? Table of contents. And this allows you to get a glimpse of the contract as specific to the implementation, but the details for the implementation is not inside the interfaces. This allows developers to provide a consistent set of methods and behaviors, right? And just simply just describing what the behavior is to the applications. So this application is the concrete one, right? Implementations. And the interface is abstraction. Abstraction. Okay, so during we talked about interfaces. Let's move on in the next slide to talk about stack.
All right, folks. Any questions about this? This is sort of the continuations of chapter 1, and something that you might have known already. The interface is for implementing. The abstract class or classes is for extending. Okay, there's difference between interface and inheritance. All right, and if you look at since we're on the topic, chapter 1, where we talked about, I think there were some homework assignments there. Let's dive into it. There's no interface here. That's because we have already defined what a stack is. So for problems like this, I would say for most of the homework assignments that you receive in this semester, I'm not going to ask you to re-implement any interfaces at all. I may give you a custom interface where you would see specification of some properties. So let's say, hey, this iterator class would have a has next features, and I want you to implement it. And that would be part of solving a specific problem in this class. But I'm not going to ask you to define a brand new data structure, if you will, starting from an interface. That whole interface idea is part of the ADT understanding we need to have. Because when you get into Java, even when you use Java util, which is what we collectively call it as the Java collection framework, where you see a whole bunch of data structures in it, you will have to read their API and understand, what their interface is about. And Java C collection framework is pretty complicated. So you have to have this level of understanding, right, on an interface level. So this is probably the last time we're going to talk about ADT in general, or its mechanisms. But then every week, you're going to look at brand new ADT for brand new data structures, and then get 20% of that ADT properties and behaviors in mind to have some ideas of how you implement that data structures moving forward. Okay, so that would be the kind of the ADT implementation compositions of each week's lecture. Any questions so far? All right. Yeah, let's talk about interface polymorphism. This is an example that I wanted to illustrate. Again, towards the end of many intro Java classes, you'll probably see something like this, where the lecture topics evolves into interface and inheritances. With respect to interfaces, you can implement them, right? So a lot of times you can have an object, and if you want to make those objects, to assume specific behaviors, you would implement some interface. So the example that I would illustrate here is if you to create a dog object, that dog object or the cat too, right? In general, they have to have some sort of common animal properties, meaning cats and dogs, they all have 4 legs, right? Or maybe some animals with 2 legs, right? Whatever the case is, you can define these interfaces like animal generic interface, right? And you implement them, right? So that's the idea of a dog or physical dog or physical cat is akin to having a physical data structure, a data structure that assumes specific properties. And those properties will be the interface we're talking about here. So without further ado, let's move back to the previous and look into this video.
Let's talk about interface-based polymorphism here before we get into stack. Well, the reason why we're dealing with interface-based is because typically polymorphism deals with concrete classes through inheritance, right? So polymorphism means many shapes, many forms, or many phases. It occurs when we have many classes that are basically related to each other through inheritance. But in this case, they're related to each other through interfaces. So what does that mean? A variable declared to be an interface type T can hold a reference to any object class that implements that interface. So this is a very interesting observation because we're going to keep using this interface polymorphism throughout the entire class, right? So if you have a figure, right, interface, this is what we got from the last lecture, right? And essentially what you have here, right, is that you've got, this is a circle, and then you got this rectangle, right? Just say rec. But let's say you've got an array of, you can also create an array of figure interfaces. So figure interface. So this is an array of figure interface instances, right? What you can do is, because this concrete implementation implements figure interface, you can also have a circle in there. Let's say circle 1. And here you can have rectangle 2, right? And this is rectangle 1. So this means that at runtime, you can have an array of interfaces. This array of interfaces of type figure interface can hold circle instance, rectangle instance, or any instances of type circle or rect, because both circle and rectangles implements the figure interface. This is what how this works with interface-based polymorphism. So let's look at specific examples in the next slides. So as you can see here, what we got is we have an array, right, of figure interfaces here. So that's called figure. So what you can do is, at some point, because both circles and rectangles implement interface, the same figure interface, you can slot them into this figure array. This is what we call interface polymorphism, okay? Interface-based polymorphism. Now, because polymorphism is dynamic binding, right? Dynamic binding. So this is late binding at runtime. This means runtime. This happens at runtime, okay? So there's also static polymorphism, but we'll talk about static polymorphism later on. This is not important with respect to interface-based polymorphism. So this means that the binding of, right, the determinations of what's happening at figure 3 happens at runtime. Because this happens at runtime, we can't really tell, right, at construction time, meaning statically, like right now. So whether figures in index 3 is a circle or rectangle at construction time is immaterial, right? We don't know, because this is a polymorphic object based on interface-based polymorphism, okay? So we're gonna see things like this throughout, and these are implementation details now, throughout the entire course of this semester's. So I just wanted to reinforce the idea of what an interface-based polymorphism is in the context of this class.
All right, so let me summarize this, right? So if you look at, or maybe not summarize, if you look at what's on the screen, it says what is held in figure 3. Obviously, if you just look at the logic right above, you kind of know already, right? But but I guess the premise behind this question is you're not the original developer. You don't have access to code, but you have access to the data structure. You don't know what is stored inside that container, period. Because a lot of what goes into that container gets constructed, right? Inserted at runtime without you knowing, because you're not the original developer. You don't have access to code to see the logic of what gets in there at figures 3. That's the point. Make sense? Any questions? All right. I think this should be a sufficient material for us to get into data structures in general. And if you still have questions about interface, polymorphism, how interface works, this is not really inheritance here, okay? We don't deal a lot with inheritance, which to me is more of the applications of making use of data structure to build something else. But our key focuses here is to define and implement our data structure so that we can use it to solve problems. All right, so no inheritance in this class, no exceptions, no handling exceptions in this class. Your focus should just be on how a data structure is constructed and what that is in general, so that you can apply the knowledge, the fundamental knowledge about what that is to solve problems appropriately. Okay, computing problems. All right, I will leave you at that, and let's move on to the next materials, which is 2.2, I think. Yeah, stack operation. Okay, now that we formally get into stack, as soon as we go through this intro stack, I like to get into more details of how stack really works and what that is in the references, so that we'll complete this study here. So a stack, as you saw in your homework 1, which is the optional homework assignment that I gave you, you see a whole bunch of operations like push, pop, peep, talk, write, is empty. So these are typical, what I said, transformers and observer methods inside a stack operation. So these are properties or behaviors of the stack. And push and pops are the most common transformer ones. Transformer methods in the context of this class means getters and setters. No, actually setters. Setters as in methods that's going to change the data, okay? Observer will be getters, or checking to see, to observe whether data has changed or not. So another way of putting it is transformer is write, observer is read. Okay, so a typical data structure has both read and write properties. And that's what we're going to look into. Let's take a look.
Stack is an ADT. So it's not a data structure. ADT is abstract data type. So stack is an ADT in which items are only inserted on or removed from the top of a stack. A pictorial representation of it includes a stack of cafeteria trays, a stack of coins, a stack of boxes, a stack of shirts. The property associated with a stack is last in, first out. The very last one in is the first one out. And so if you to push something in, this is push. You put another shirt on top of the original stack. But when you want to remove something from a data structure, from the ADT, you will pop it. The top one, which is the last one in, is the first one to go out. Okay, so this is what a stack is. Let's move on to some of the high-level descriptions of operations. So in a general stack implementation, you have three tuning types. One is the constructor. Constructor is the point of entry in creating or instantiating a stack. It doesn't have to be an empty stack. It could be a stack with already stuff in it. This is the constructor part of the operations. The second part is what we call transformers. A transformer is just a whole bunch of verbs. These are actions or behaviors that effectuate changes inside the stack. There are two operations that are common to stacks. One is push and the other one is pop, which I just talked about. And the third one is observer or observations methods. These are methods that peeks into the state of your stack. You could also have an observer call isEmpty. So there's several types of observers out there. These are typically just read-only operations. And transformers, these are mutations that effectuate changes to the stack. So anyway, these are just CS terms that we use frequently to observe these things. So let's move on to the next one. The effect of a stack is, so you start up with, let's just look at the top one. There's nothing here. The very first element gets in when you push the block 2 into it. So top becomes block 2. So top always points to the top of the stack. This is an observer. Push and pop, these are transformers. So we keep pushing stuff into it. The new
to go out, last in, first out. So bear that in mind. Let's study something more about the stack. Let's move on to the very next.
A memory address itself is an integer. So you can think of the entire call stack like this at runtime, sitting inside of your computer memory, responsible for aggregating integers. And if you look at this, memory address and content, you can think of it as a call stack that we have on the right side, where each frame contains the memory address and the content sitting inside of it. So this content holds the memory address of whatever was inserted at runtime. And because stack is last in, first out, we need to have some sort of pointer that constantly points to the top of stack. So this is also called top stack pointer. And this top stack pointer keeps track of the top positions at any given moment, meaning when you start to insert or push information into your stack goes up, your top pointers will be moved accordingly. Whenever computer decides to release information, that's what we call pop. This information then lowers the top pointer because as you pop information, your stack pointer moves down in this fashion. So this is push, this is pop directions. Let's move to the next page to illustrate how this is relevant to passing arguments into a function.
All right, folks, that's call stack. Any questions? Let me see how far I wanted to go. Yeah, I think this one, very next one, also kind of illustrates this. Now, this is all inherent in C++, but in Java too. In fact, in any programming languages, how computer utilize stack to kind of quote unquote remember what it transpired in terms of the sequence of calls and how computer memorize and remembers, right, data in the past. So this is a that push pop operations in the opshots. Let's take a look.
We are going to talk about how passing arguments into a function has anything to do with the call stack. I'm going to draw a call stack on the screen. And this call stack is positioned vertically as before. This is an empty call stack. So the very first element will be pushed into the very bottom of the call stack. Initially, the top pointer points to the very bottom of the stack as it is empty. Let's step away from this call stack and talk about pointer. So remember, in C++, a pointer is a variable that stores the memory address of an object. Pointers are used extensively, right, in both C, C++ for three main purposes. One, to allocate new objects on the heap. Two, to pass functions to other functions. Three, to iterate over elements in arrays or other data structures. So we're going to see that over again. Let's talk about pointer. This is the memory cloud inside your computer, and your pointer may be occupying this particular space. And since pointer is an object at runtime, it itself has its own memory address and a size on the stack. So if you look at this entire block occupied this pointer, the size of this pointer could be ascertained by way of size of and whatever this pointer is. Let's say PTR. On a 64-bit computer, it usually leads to 8 bytes. And this pointer, by virtue of sitting inside this memory, also has its own memory address. And let's say this memory address is 0 times FA2. So there is a lot of information about a pointer. Not only that it has a memory address, this pointer also stores someone else's memory address, namely the address of another object. All of these informations will be stored on the call stack. Let's see how that is done. We will wipe out what's on the left and keep what's on the right, and transition to the next page. In this example, we're going to illustrate the effect of push and pop into a call stack. Let's just assume that we have a stack pointer, and this stack pointer is pointing to memory address 100. So for the sake of illustration, we will say that the memory address starts with 100 and it decreases over time. As you can see here, it starts from 100 to 0. 100 being on the bottom of your call stack, which is the very first element. The second element will be at memory address 99, so on and so forth. There is a total of 101 elements inside this call stack. Remember, your very first top points to on the bottom, which is at 100. And this call stack that I draw on the screen is analogous to what I have on the left. As soon as you add a number 4 into the stack, we're pushing a value 4 to it. This causes the top pointer to move up, namely top now points to memory address 99. And by saying that stack pointer decrements by 1, the memory address now moves to 99 because it was 100. So memory address goes down by 1. This value of 4 sits inside the activation frame. This illustrates pushing a value into a call stack. Let's erase the left side and move on to the next procedure. Let's add another value or push another value to the stack. In this case, we will push a value of 33 to the stack. In so doing, our top now points to the memory address of 98, as illustrated on the left here. Let's move on to the next step. In this example, we're going to remove number 33 from the stack. Notice that top now points to address 98 with a value of 33. So what we need to do is to remove 33, which means popping 33 off of the stack, as is illustrated here. The value of 33 remains in memory address 98. What does that mean? Well, that tells us a couple of things. One is your program is not going to actively pop a value off of the stack. Popping a value off of the stack simply means moving your top pointer back to where it was. Now, because your call stack maintains the address of each activation frame, your top pointer only needs to move up and down depending on whether you're pushing the value into it. In fact, when your stack pointer goes back to the previous address, 99, the content sitting inside of 98 is still there. There's no need to erase that 33 or the concept of removing that value off of the previous address. Now we know how activation frame and call stack works mechanically. In the next example, we're going to illustrate a code snippet and how call stack works with respect to passing arguments into a function in that code snippet.
All right,
we're going to talk about.
Sorry, we're not gonna get into it. There's actually more. These are references I want you to go through. So maybe in your spare time, yeah, you can look at this other one. So they're basically illustrating how, when you create a console application, these things get pushed and pop, into the call stack, which is part of your memory structure, and your CPU, your processor, and your code is responsible for pushing these data into it such that your program remembers, right? These global variable, local variables, and how they intertwine with each other. And that's where stack is in action. All right. Not in your textbook, but I wanted you to, to go through them and really kind of get a context behind why we're using stack, what's so important. All right. So here comes a couple of external examples. That is where you see stack at play. Web browser makes use of stacks. Your word processor, when you use Microsoft Office, and even your code editors, sometimes, if you guys know, like Control Z, Control V, Control C, especially Control Z, which is undo, or Shift undo. Sometimes people, I don't know, depending on the operating system, maybe Control Z. The feature of undo is built on top of the stack, right? Last in, first out. So when you do something in the word processor, let's say you type in something and you do undo, the Microsoft Office seems to have remember, right? It's what you just did, and you just keep on doing undo, and you will see the step, prior to what you did. And those things information is stored on the stack. But stack can only be so big, so it's not like you can infinitely undoing what you do. Keep going. Sometimes maybe 10 steps ahead or behind, or maybe 20 steps. And then there is another feature called redo, right? Where computer kind of remember what you just undid, and you can go back to what you undid before. And this undo and redo, these all play out in the context of stack. Your computer actually remembers this via stacks. And if you look at a whole bunch of other stuff like networking, even networking has undos and redos. And these are protocols that are stored inside your computer. And this will be on the sessions, probably a session layer, which is, I think, the OSI layer number 3 or number 5, sorry. And this has something to do with your networking class if you haven't taken it. Operating systems too. Memory management, we already talked about. It's definitely using stacks. Web development operating system. Yeah, I think there's a whole lot of these stuff. Not getting into it since we just go over it, and there's a 2-minute video. You guys can view it on your own. Any questions so far? All right, so now that we know why we're studying this, let's take a look at the specific implementations. That's what we wanted to get to. All right. So since we started the class 5 minutes in, yeah, let's go through this collection elements and then we'll take 5 minutes break. Okay. All right. This video starts the discussion of collection. Yeah, this is an ADT and an object that holds the other object. So stack is kind of a part of it. Stack is also part of what's called list ADT, but that's something that we're going to talk about in 2 weeks. So let's quickly look at this video.
We'll talk about collection elements as they relate to stack. A collection is an object that holds other objects. Collection is an ADT in computer science, and stack is an example of a collection ADT. Collection is an object that can hold many other objects. So these could be objects of the same type, or they could be objects of different types, right? It depends on how you define your collections. Generally, we're interested in collections operations with respect to these objects. They're same objects or different objects. You can insert them, you can remove them, you can also obtain the elements of the collections and things like that. Now, stack is a collection ADT, right? It collects many different elements and it follows this first and last out ordering among the elements. Let's look at how we can implement stack, right? There's different types of elements. If that's the case, you can have multiple types of stack. You can have, like, for example, so 3 elements. One of them makes use of a string stack. The second one makes use of integer stacks. And the third one makes use of this custom bank account stacks, right? So you can create these collections out there. And they're basically just an array, right, of these object types in it. Now, the problem with this is this one is not very scalable. In the future, when your code calls for several other ones, then you have to modify your code. This is very bloated. Your stack is not cheap, right? So when you want to keep making up new ones, and plus it's not very easy to maintain codes like this. When a new object comes around, your stack for that or a collection ADT for that object calls for a brand new implementation of your constructor, your transformers, and your observer. Let's look at the next one. Another idea is, why don't we just make use of inheritance, right? This is the traditional polymorphism, where you would have all of the classes inherit from this object. So this object is going to have a stack. In this case, you can have string, integer, or integer string, because everything inherits off of the objects, right? So these are inheritance because it uses a solid. This is a solid arrows. The solid arrow means inheritance. Okay, so we went through this in our UML lectures here. You can have one object stack, or you can pump in either string or integers or several of them all at the same time. When you pop something off of your stack, something comes out. But how do you know if that element popped? Is it an integer, is it string, or bank account? You don't know, right? Because everything is part of the object stack now, polymorphism. You have to keep track of that metadata associated with that type of concrete class that you're interested in, making sure that you cast that information when you need to use that object when it's popped out of the stack. So this is what we're talking about. When an element is removed from a collection, it can only be referenced as an object. So you need to cast this, right? So in this case, you have to remember to do that. And this is very cumbersome because you don't know unless you preserve that information inside of the element, then you can cast it correctly. If you cast your information to the wrong type, you're going to get some runtime errors. It looks to be pretty scalable, right? Much better than this approach, but because of the accounting there, you have to keep track of. This is simply not very safe methods. So this other methods is what we call interface polymorphism. You would actually have these concrete classes, like in this case, monster, heroes, and treasures. This is implementations. Implement this particular interface. So you can create this drawable collection, like I said before, this array of interfaces, and you can pump monster, hero, monster, right? These various different concrete classes that implements it into it. This will work for specific situations, but it's not a general solution. Why? And the reason is because sometimes you can have multiple interfaces being used by others, and some of the concrete classes may not have the correct implementations. every time you do implements like this is defining upfront. This is static. Your static implementation, right, has to basically hard coding. It works for specific situations or to the extent that you have it hard coded, still not very general. And this is the power of Java generics. So generics is a concept that has been around for about a decade. Let's move on to the next slide. You can use Java generics by applying generics to a stack. And what you end up having is, and generics is indicated by these bracket notations. What is inside the bracket notations is an object. Okay? So because we're dealing with objects, this cannot be a primitive int, right? It has to be an integer class. So this has to be a class or type objects in there. So the idea is that once you pass the generics into the ADT at construction time, upon instantiation, this generics will then be a part of the class. And this allows you to specify the type of your array. So in this case, at construction time, because you're parameterizing it as a T, this T is the decorations. At the implementation time, this T is actually integer. It gives you this stack, array of stack of integer type. And because you're declaring this is an instantiation time, this generic is of type bank account. It gives you this stack of bank account type, so on and so forth with string as well. And this generics is typically annotated by this letter T. T stands for type. And the actual type is provided upon instantiation. So one example is I can do this string, assuming stack is already there, right? And then you can genericize it. You can say, I want string. This is S equals new stack and string bracket. You can do this dynamically. This allows you to instantiation time to create dynamic array of concrete objects that implements stack. This is interface-based polymorphism that we're going to see repeatedly. Make sure that you understand what a polymorphism is and how generic works. I would say these are the two important topics that you want to refresh yourself on in order to make use of the examples, understanding the example better in this course.
All right, folks, any questions about collection elements? Yeah, in a couple of weeks, we're going to look at collections ADT and list ADT, where we talk more about these collections in general. But it's just that this also applies in the context of stack. All right, let's take a 5 minutes break. Let's be back at what is it? 10:12. Okay, and see you back in 5 minutes. All right, folks, time's up. Let's go into 2.3. This is part of your studying chapter 2, section 3, generic collection. So we talked so much about generics. Generics has been around for 15, maybe 20 years now. It is an old stack, but it has been around and for so long. And you see them in other programming languages as well. Let's see how this generic programming paradigm is applied to Java and also is used in data structure. Very quick video.
Let's look at generic collections or stack. If we're going to use generic, by passing in this type T, generic uses this notations here. What we are doing here is we're creating an array of a type T. This is dynamic late binding, dynamic polymorphism. This creates an array of interfaces. These interfaces of type T could be of integer, bank account, string, or any custom types that you want. This also means that, at late binding, you're associating only one type to it. You cannot have an element associated with an integer, bank account, right, string. You cannot have multiple types into it. You can only have one. This stack only has this type sitting inside of it. And you don't have to worry about casting this information to multiple. So none of that. This is the beauty of using generic inside the collections. Also, you can write this as dynamically, let's say, integer stack, instantiate this using this, and you can write out the whole thing. You can actually leave this one too. Okay, so this is default constructor. If you leave this as is, meaning don't have integer in it, it will take the primitives. But if you push integer, this class in, then you can take both integers and primitives. So the second part is actually please, it's optional, but you can also have this in as an integer. This is how you dynamically create an integer stack.
All right, very straightforward, folks. And I think there are some examples, and you're not going to find this in your textbook. Yeah, it will be the coding example. But before we get into the coding example using generic, let's look at stack interface since we talked so much about it. And now we introduce collection, we introduce generic, and let's see how this stack interface is constructed.
Let's talk about the stack interface. Recall that stack is a last in, first out ADT. A stack is not a data structure. It is ADT, abstract data container. And it has three major transformers. These are our mutation methods or operations. So one of them is what we call push. This allows you to add an element into the stack. Pop removes the elements from the stack, right? This is last in, first out. If you have a stack like so, push is responsible for shipping your elements into the stack. So you can keep adding your elements to it. So these are pushes. Pop allows you to pop the top elements off of the stack. Last in, first out. So this is pop. You also have what's called top. Top allows you to peek into what's out there and returns the top elements of the stack. If your stack is empty, your top is going to throw in an exception. We're using a generic stack for this interface. This is the interface. Java generic is one of the most important features introduced in Java 5. We'll get into more details about those. There's also a constructor that creates an empty stack. This is all necessary in this interface. Let's move on. There's a couple of error handling that you're going to have to do for pop, top, and push. Stack overflow exception. This is the custom exceptions that comes with your code. Let's say if you have an entire stack is empty and you try to pop something or try to fish the top element for an empty stack, you're getting the stack overflow exception. Let's say if your stack, on the other hand, is full, you cannot push any more elements into it. In that case, you get stack overflow exceptions. This is the reason why we have the observer methods. There are two of them. One of them is the is empty and the other one is full, to constantly hold this in check. Don't ever go out of the boundary. So this is a generic interface in Java. Please study what this interface is. It's in Java if you don't know what it is, and also study this generic type. So just to summarize this, Java generic type helps us understand code easily. This gives us the ability to compile time type safe checking. And normally, when you see this in the context of either an interface or class in Java, it's usually parameterized. There's a lot of conditions associated with this. For example, you can use this as in Java inheritance as well in polymorphism, as we see from time to time in this class. We will give an example of the use of this generic stack interface through use of this demo.
All right, folks, any questions there? Stack interface. You'll see your stack interface code. In fact, if you scroll down, there's a code section. Now, all of these snippets are straight out of your textbook, but I did make some modifications because in your textbook code, they use package just so that you can compile whole thing and set up specific folders for it. I eliminated all of that, and in fact, if you just copy and paste these code snippets, these are complete code, not snippets, into your IDE and set up your own structure. You can compile them, okay? Or for the purpose of this class, you can just look at them. It's not required for you to compile these things, but a lot of what I refer to, specifically the implementation details, are all in the call, okay, in these files. And yeah, I got rid of the package here, but everything else is the same. All right, there's some. I'm not gonna say, let's just say this code, is never in my mind top quality, and there's some, I guess, inefficiencies surrounding the use of global variables here, but that's not focused on the efficiency of the code or the quality of the code, right? These are written by instructors of the book, and they have their own design thinking. So that's more focused on the functionalities of what's covered in the code, okay, and also in the book from a concepts standpoint. Questions? Cool. All right, we talked about generics, so let me put up a demo. This is not your textbook. This is what I did from my IDE. So let's take a look.
This illustrates the difference between a traditional non-Java generics, a way of implementing a collection. So what you're looking at is a free online website. This is an online IDE. Execute this. This hello world works. So let's just start off from here. I keep calling it this hello world. I like to enlist the use of an array list. This is typical Java collection APIs. Import this as well. You can do a util star if you like, but I like to just import what is needed and nothing extra. We're going to make use of this to illustrate the collections implementation. Let's create a stack. In Java, you can use array to create a stack if you like. So array list is a dynamically sizable array. So once you have this, you can keep adding items to it, right? Right now, this list is empty and there is no specific generic types associated with it. This means that you can push any Java object into it of class object. Everything is an object in Java. So you can push in, let's say Java, right? The entire string itself, this instance is a Java object. You can also add, for example, a new integer, let's say 8 to it. This is good. And this is also good. Let's compile this. This works. So if I were to, let's say, iterate through this, you can do that with object, let's say, through the list, right? So this is going to give you the two objects that you just inserted. But the problem here is you don't know if this object coming out of this list is integer instance or a string instance. If you do something like this, for example, a string s equals, try to cast, because you don't know what this is, and you try to do that. This will work for the very first one, but it will not work, obviously, right, for the second one. So let's just see what happens if we execute this. And you can see here there's a class cast exceptions. So this won't work. Can we use Java Generic to fix this? It turns out we can. So Java Generic came out in 2004, Java 5. So in order to turn this into a generic version, so you can say, remember generic starts with this angle brackets, right? And you said, I want this to be a string only. So what you can do, you can say, I want a type safe string. So this list moving forward at compile time knows that at runtime, it can only take string instances. This won't work. In order to make this work, you can simply just say, hey, this is not an object, this is a string. Then you don't have to type save, you don't have to cast this anymore. If you like, just print them out and see what happens. So let's compile this. This works. We just assign a generic type, compile time, and this type safe. Moving forward, you can push all of the string instances into it. But let's say if we don't, instead, we decide to do something like this. Is this going to be okay or not? When you execute this, no, it's not, right? And this is pretty obvious because you're telling this entire collection to accept a string at runtime, meaning all of the elements inside of this buffer has to be a string. And now you're putting integer into it. So you have to comment this out in order to compile this. These are the two quick illustration of the non-generic collection versus the generic collection. So ultimately, you can call that collection stack. Okay, stack is just an ADT. We're talking about data structure here. Okay, so hopefully this illustrates the generic versus non-generics.
All right, that is generics, but in general, everything in Java inherits off of what's called the Java object, capital O, right? And you study this in Java. So technically, you can cast everything. You can genericize everything to object, or you can create an array of object or any container of object, Java object. And but the problem is you don't know which type is associated with that. Anyway, that gets into kind of a design decision. But the key point here is when you create these container or data structures, you have to be careful of what types of object or data you store, and you make that decision upfront on the interface level, so that moving forward, that entire data structure that you implements the the genericized interface would be the key, right, for storing data. If that whole data structure is implemented using an integer, interface, or at least the types associated with integer, then you can only store integer. Don't store strings and other custom data in it. So you make that decision, and in order to be flexible, use generic. Okay. Any questions about this? Should be fine. Yeah. All right. Here's a code demo illustrating how string is reversed using stack ADTs. This is just another example, not in textbook, but this is a very common interview problems too. How do you reverse a string? And you can do that with a double pointer approach, no storage. But in this case, we're going to use stack, and stack is a storage. So there is a memory consumption and requirement for it if your string is really large. Let's say a string with 1 million characters involved. In order to reverse that entire string, making use of stack, that's a lot of memory you have to store. But then again, it actually makes your code a lot simpler. The fact that you have a data structures involved, right? Last in, first out. So let's take a look how this works. It's very quick.
Let's go through this reverse strings.java. This is an example from your textbook. I also mentioned this is in the lecture briefly. There is an import. So do not worry too much about the package, so to speak, because you won't be able to compile it without that package. But just looking at the code here, line 17, 18 here, this is the interface-based polymorphism. So we talked about how this works. So you can use an interface, and this array bounded stack. It's a concrete class that implements a stack interface. You can create an interface wrapped around this concrete class. This allows you to push in the generics. This generics is implemented in your stack interface as well. This type safe string goes right in there, and to ensure that all of the elements are needed to be instantiated as a string at runtime. Looking at this, so what happens is in order to reverse the string, let's say this string is SMC. So you want to push that SMC, this entire string, one at a time. The string is coming from your line. This is user input. So enter a line attack. This entire line will get pushed right in. Let's say there's 3 of them. The first one is S. That's the first line. Let's just assume that each line has 1 characters in there, right? So the first one is S. The second one is M and C. This is the stack, a string stack from here, from this point. You have this SMC now. In order to reverse the string, it's pretty easy. All you need to do is once you're done pushing all of your string into the stack, you said, I'm going to start popping this off, right? So you invoke this pop methods on the string stack, checking to see if the string stack is not empty, then you can keep on popping it. So when you pop it, it's gone. You want to do a top first. First one, you want to do a top, and then you want to do a pop. This allows you to print the popped string off of the stack one at a time in reverse order. So this is how you reverse a string making use of a ADT. This ADT happens to be implemented using an array. So hopefully this illustrates that examples.
That's your textbook version, and you can find the code here. Okay, not that example, but you can find the stack, the array bounded stack examples in it. All right, let me see what else is there. There is a Java call stack example that I put together. I think we still have some time. Let's take a look.
Let's look at call stacks, which are also known as activation records. This is a data structure that stores information doing program execution. So a stack is kind of like an array. Right now, we're looking at this from vertical standpoint. So these are actually slots, where the very first slot stores I equals 5, second slot stores j equals 2. Call stacks in general have last in, first out property, which means the very last item that goes into a call stack is the first one out. So if you look at this being the very first item that goes in, K being the very last item, if we were to pop a record out of this call stack, K would have been the first one to go out. In the next couple of frames, we're going to look at an example call stack when a max method is called. You'll see these values going in and out of call stacks until the program is complete, in which case the stack becomes empty and your application is done. An activation record is essential for supporting the execution of methods in most programming languages, especially those that allow recursions and function calling other functions. Activation record is created and pushed onto the call stack each time a function is called, and is popped off of the stack when the function returns. This is the reason why when function returns, the stack is empty. Let's look at how a call stack works. You have a main function. This main function has a couple of initializations, creating integers I and j plus k, and there is a method invocation. This method is a static, which is basically a function that has two parameters, comparing to see which one is the biggest, and returns the max of the two. So since your main is the point of entry for a program, the very first element I is stored inside an activation frame or a call stack. This is when main method is just invoked. Let's look at the next frame. Now that we have j equals 2, remember a call stack is last in, first out. J is stored after I in this fashion, so our call stack actually grows vertically top. Let's look at the next frame. Now that we have k, remember k stores the return value of max methods. And since k does not have anything before the max is complete, we simply store this value k here, and the value is undefined. This is what happens when you just declare a variable. Upon declaring k, we have this assignment, which then invokes the L value, which is your method, defined here. Let's look at the next frame. Now we are at a function invocation. Both your I and j's are the arguments passing into this max function as parameters number 1 and number 2, respectively. Notice that when the function is invoked, nothing needs to be stored. Technically, each function has a function pointer, or the memory address associated with that function, and that memory address is stored inside the call stack, but it is not illustrated here for the sake of simplicity. Let's look at what happens next. Now that your num1 and num2 would take the value of I and j, respectively, these parameters must be stored. These are what we call the local vars, local to your max function, which means num1 and num2 is not going to be known outside of this method. Therefore, as your flow of control continues, num2 bears a value of 2, num1 5, and they are pushed into the stack in that order. Num1 goes first, num2 goes second. So now you have a total of 5 variables, I, j, k, num1, and num2 in your call stack. Remember, your growth of stack is up this way. Let's look at the next frame. Note that your flow of control is inside this line, calling for integer result. Notice that this result is only declared, so we push that key into your call stack with a undefined value. In Java, an integer variable has a default value of 0, but since we don't illustrate it here, we're just going to leave it empty. Let's look at the next flow of control. Next, we have conditional statement comparing num1 and num2. Let's clear this. There's nothing to be stored because we already have num1 and num2, as these 4 lines calls for evaluation, not storage. We know num1 is 5, num2 is 2 because of I and j values. So this line is evaluated, results equals num1. As soon as this statement is evaluated, result has a value of 5 due to this assignment. So we push that 5 into the result in the call stack. Let's clear this and move on to the next frame. Next up, your flow of control is about to return your results back. Notice this is a little tricky because now that we have results equals 5, and this result is about to be assigned into the value k as your function max returns. As soon as this returns result is evaluated, a couple things happens. Remember, you have num1 and num2. These are local variables to max function, and both these variables will be out of scope, meaning they will get popped out of call stack as results exit. So this thing will be popped, and num2 and 1 will be popped one at a time as your function exits. And because the value returned from max, it will be assigned into the value of k equals 5. Now your entire stack remains with these 3 values. Call stack is last in, first out. So as your flow of control returns from max, we're popping these one at a time. Let's move on to the next frame, or the final frame. Now that we have system out printlined, notice that the entire call stack portion calling for num1, 2, and results are gone. Now that we're left with k, j, and I. And these values are used in the very last line of your main. The system out print line is complete. Your k, j, and I will be popped off of stack in that order. And then your stack is going to be empty again. This is how call stack works, using this main console application invoking max function. There's a couple of other references included in this topic. You may reference those examples for more information to glean insight into how call stack works.
All right, folks. A couple things to note. Now, if you look at this entire call stack or activation frame, what happens in the computer? Your computer actually doesn't pop those values. So pop is literally just a name for, hey, I don't want this value anymore. What actually happens in computer is you see those pointers, right? Pointing from one to the other. Your pointer simply goes back to the previous one. So last in, first out. And those elements are supposed to be popped. They're actually stored still in memory. They're what's called unreferenced. Okay, you guys know what the meaning of an unreferenced data is, right? It's fate. In Java, unreferenced data gets garbage collected. There's like sanitization thing that goes on. You know, there's a mechanism called GC, garbage collections, goes around and claim literally dead bodies on the streets. And they are swiped off. Your pointer doesn't do anything. Your computer doesn't say, hey, right now, this thing is popped, so please clean it up. They actually get queued up. There's a separate process called GC collection, right? Garbage collection. That's all happens behind the scene. Now, what happens in C++? There's no GC, right? So these unreferenced data, they simply strewn all over the place in computer memory. So if you look at the entire, memory space, let's say you take you have this uncanny ability to look into your ones and zeros in computer memory space at runtime, you see a lot of quote unquote garbage strewn all over the places that are unreferenced. but that's all fine because your pointer, right, still pointing to what's needed in this entire call stack. This is the reason why in computer science, a lot of times, when you run or try to allocate something that you accidentally take control of someone else's memory spot, and that happens in C++, you create computer crashes and things. And when you reference an area where you're not supposed to, you be claiming some leftover values stored by some other applications in general. So these are true, when you started exercising, your application for anything in general. So just be careful. Anyway, so what I just stated there kind of goes outside of the scope of stack, but I wanted to keep you abreast of what stack really works in terms of activation frames and call stack in computer memory. Okay. All right. Any questions so far? Cool. This portion is not in your textbook, but hopefully you can put everything in together. There's some references here I told you about. You should go through. In terms of stack, yeah, for some reason I didn't include array implementation of stack. So maybe let me double check. They might be going into next week's. So in the past, I spent a lot of time on stacks, and today I think we're slightly fast. And if we don't go over today, we'll have to go over it next week. So let's just make sure we still have time for it. Yeah, there's some. Hold on a second. So next week is going to be linked list, stack variation. So the reason why I did that was because if I had to go over linked list in there, linked list is like another topic, and it takes forever to go through. So I decided to separate them. All right. But if you go back and look at this, I think the only portion what I didn't include was the array bounded stack. So why don't we just take a look right now? This is your array bounded stack implementation, making use of stack interface generic. And here we see two constructors. The very first constructor says, hey, I'm going to create an array of certain capacity. So this is default capacity, def cap. And that is set to 100. So you have a default array of 100 in size using this default constructor, or you can specify the size of your buffer. So let's just call these things buffer. Stack has a buffer in it, and this buffer is implemented using array. So that, then you have push and pop, right? These two transformer methods that essentially sets value or write into your data, push and pop. It changes the state of your code. So we call them transformers. And then you have top and is empty, is full. So these three, they don't change the state. Actually, top is the transformer because it actually pops the stuff off of the stack and returns the value of what you just popped. Hold on a second. Let me see. No, it actually doesn't because there is no changes to the state of your elements. There is no plus plus. You're simply just reading off of this, returning what you see. So it's kind of like peek, peeking into what's on top of your stack. So top is empty, is full. These are what we call observer methods because read only. Okay, you don't change the state of your code, your machine, but push and pops of transformers. So these are the methods that we need to look at. In your homework assignments, you don't have to worry about Stack Overflow, Stack Underflow, because your problem will specify the constraint. So you never go outside, right? These boundaries, you have to care about error handling them. But if we look at push, if this is already full, then you can't further enter additional data into it. Now, if your entire stack is empty, then you can't really pop anything off of it, right? So these are two exceptions. But otherwise, every time you pop your elements into it, you create it, you add on top of your top index. So you keep track of your index location. So going back to the example that I gave you earlier, where we have this entire stack, right, that goes up. So your top pointer initially pointing to index 0, right? Later on, when you add more to it, you got a plus plus, okay? So that whole plus plus is referenced by your top index right here, which keep track of, whatever the current position is you are in the stack. Pop does the opposite. It actually alleviates your pointer from keep going up. It instead drives your values down. This is a push, okay? And the other one is pop. All right, so pop actually decrements the top index. If you do this in one line, you can actually use the prefix minus minus top index, and then the same thing with plus plus top index. That way, you can get the elements out and decrements it. Okay. Hold on a second. Let me see. Top. Actually, you want to use you want to use prefix. You want to make sure that the top index is adjusted, and then you can do the changes later. Hold on a second. Let me see. Null, nullify, and then you minus minus. Actually, you want to do a suffix here for top index. For top index for push, you want to do a prefix. Okay, so one of them is a prefix, and the other one is suffix. So there's actually a difference between the two, and you can do that here, and to save 2 lines of code, to consolidate 2 lines of code into one. All right, any questions about push and pop? All right, yeah, I don't think we need to spend a lot of time on the top and is empty. So basically keeping track, right? If the index is at -1, so you gotta set index to be -1 as a default. Setting this to a -1 is not something that I would recommend. Usually, you wanna create a unique constant and set it to it, so that you can use it to reference. Hey, there's nothing there, and is full is when you get to the capacity of your array, because we're using array. Array is an object in Java. Okay. So when you create an primitive array, it is still an object. And as such, object has its own property called length. So you can elements.length. Elements is your array. Make sense? So this is array implementation in the abstract. Very, very simple. And linked list is on the other side, where you have to create linked lists and then, of certain size, and it gets convoluted. And then we'll do a comparisons between array based and linked list based. Array based subject to a limitation. What is the limitation of using array as a stack? There's actually a lot of limitations. As a matter of fact, there used to be a participation activity. I didn't publish it, but array has a problem. And that problem is array is fixed. There is no such thing as dynamic array. There is, but it's more on the mechanism standpoint. You can dynamically expand the array, right? But array is fixed in size. So what is the solution for it? Let's say if you run out of stack, the next obvious things to do as a software developer is you would dynamically expand the array, right? But since array cannot be by nature expanded on its own, in the same location, right? You're gonna have to go into the computer memory and start to look for, a sufficient space that is much bigger than your original size of the array, and say, that's a new spot where I need to build my house. This house is twice as large, right? Usually expansion happens. In Java, the expansion is of the factor 1.5. But generally 1.5 to, they're about the same. 1.5 is actually the most efficient. We can actually operationally prove this in a complexity analysis, but that's beyond the scope of this class. Let's say we expand the array twice the size. So now that you double the size, now this is the brand new house, which means you're gonna have to move your old furnitures, right, from old location to the new one. And that's work involved. That's a lot of work. That's why you don't expand your array that often. You don't do that, hey, when you get to the next 100, expand another 100. That's expensive, all right? Because expansion calls for new territory. You don't just build, right next to your house. There's not enough land. Okay, this is so computer science, creating software applications is all about claiming memory space, how you manipulate your memory spaces. So in memory management, you don't just extend next to your house. You claim a spot, and usually through dynamic memory allocations. You don't want to do stack. Stack is contiguous. Sometimes you may not find contiguous space big enough for your new space. So then you use dynamic memory allocation. Still, dynamic memory allocation takes time, right? And also space. And now that you have this copying, this moving the furniture from the old side to the new side, operations involved, very expensive. But it turns out, again, this is going into a more advanced data structure class. This moving the furniture, claiming a new land, moving new furniture into a new house, this type of operation, when you amortize over time into infinity, it turns out to be O of one. So stack, making use of arrays is a pretty efficient way of managing data. Okay, so the outcome is really not that bad. You might be wondering, hey, array expansion, every time you have to resize it, professor, isn't that kind of expensive, cost wise? Yes, but amortize to infinity, it turns out every expansion is the number of adds and remove that you have. Again, that goes into some mathematical proofs we can actually get into. If you guys are interested in that topic, I am in the process of writing a book, and there's a mathematical proof associated with the average amortized efficiency of array size expansion due to the use of array as the underlying data structure. All right, I'm going to pause right here. Any questions? Okay, so that calls for the array implementation of stack that I did not have videos for. And that shall complete this week's studies. And next week, I don't want to get into linked list because that's a whole lot of other discussions. Next week, we're going to study linked list. And since we're talking about stack, we will look at how linked list is used to build a stack. And then we're going to look at stack variations as various different usage of stack, and also implementation details and the pros and cons of using linked list versus array as stack's underlying data structure. And that should wrap up next week's work. And incidentally, I wanted to call out this attendance thing. All right, for this class, as I iterated before, you are 100% okay to attend this class on Zoom without being here in person. Even though I'm here in person, you will not be marked absent for being online only. So please don't feel the need that you have to be in. And this is for a reason, because I already grant certain exceptions to students who couldn't make it. So the same treatment is applied to all students. Okay. And I would expect regular attendance on Zoom if you can't make it in person anyway. This is very important because this gives me a chance to see whether you're in class or not. And if you don't even log on Zoom, this is actually for students who's not here. There's supposed to be another 6 students. I'll send out another separate announcements to them. But otherwise, 100% okay to Zoom in. All right. You have the Zoom informations here. And I wanted to also update some of the schedules. I haven't had a chance to. I would not be able to come in next week, but I should be in after that several weeks. So I'll do this on a weekly basis so you know. And I'll send out another announcement just in case to remind students not to be next week, because I do have a travel arrangement, but I will be on Zoom and with my notepads and stuff to go through the study, just like I'm doing right now, except I will be remote. Any questions about that next week? Okay. And then you guys are cool with Zoom in person, right? This hybrid. If there's any questions associated with any of that, let me know on doing office hours or on Slack. Cool. All right, I think we talked about what's to come next week, and I will publish the module so you'll see it. And in addition to the course content online, so you can take a look at what you're responsible for. I'm not going to copy the whole, publish the whole thing to confuse you, because I want you to focus on week number 3. Okay. All right, let's quickly go over homework assignment, and then we'll be done for the class this week. Now, for every homework assignment moving forward, you're going to see this platform independent solutions. So this means when you compiled everything into a single page Java code, that entire Java code should be standalone. And in fact, how am I going to grade your work is I'll take your entire solution and stripped pretty much all of the logic except the key portion where if you look at this entire example for this week, you have your import statement, and please don't modify this, okay? Starter code means do not modify other than where you're called to, okay? You'll see the console applications here. It says homework 2, right? Console application. And console application entry point called main. And then you're going to see some class here. So there's actually 2 classes. This is what we call this is what we call the nested class. So you have a public class. This is your entry point, and the other class with no public in there. This is just Java syntax. If you put public here, then Java doesn't know which one is the entry point. So you have to put one as a public class. All right. So all of your solution goes in here. What's highlighted right now. Okay. So your class called solution has all of your logic. And how you're going to test your code is you would instantiate, right, a solution class and then call its methods, call its same sequence. Does it make sense? So I want to make sure. So like if you go back and look at, I'm going to spend a little time because this is the reason why I split the linked list out of this class, because I used to have to spend a lot of time explaining this, and I expect everyone to be on the same page. So if you look at this homework assignment, and you will see that there's a class of solution. This is your code here, right? You got to fill in your code. And then you have this entry point. So this entry point is your test, is your playground. This is where you instantiate your own solution called MaxStack right here. In the homework 2, this MaxStack is called solution. So you can create your own test cases right here in the main, all you want. My auto grader strips all of this out and tests only this portion. Does it make sense? So like you will submit one Java application that has both your playground, your test cases, and then the actual solution. My auto grader only grades your solution. Okay, only this portion. So going back, my auto grader only grades this solution here. So when AutoGrader takes out your solution, it looks like whether you have API documentations or not. That's 1 point. And then 9 point is associated with the correctness of your solutions here. Okay. So you got to read the context on like what this problem is really asking you to do, and then put your code here. Most of your code logic is here. And then you can test your code here in your main. All right. So please keep the order here intact. If you have to create any additional global variable, that's totally fine. You can create additional methods if you like, but my auto grader is only interested in this method right here. All right. And this whole platform independent solution means that my auto grader can go in there and strip your code out to leave only the solution and target that solution and test it 10 times, sometimes 20 times with different inputs. Okay. So that entire class solution is your black box, your function that you're going to have to build. And you deliver this, my auto grader goes in there and tests that thing n number of times, actually 10 times. So for any test case failures, you get -1 logic point. I actually don't implement that. As long as I see there's effort in your code, even though your solution is completely wrong, I might give you 4 points effort and then 1, for API documentation. So most of the time, students don't lose everything. They lose maybe 50% of the code, And guess what? You can resubmit it again, and then you get 100% minus some very small amount late penalty, and that's it. You're done for that week. So this is how I work, and you have until December 5th to complete your work. But I want you to submit your work on time, so that you don't have penalties involved. You can resubmit any time, infinite number of times before the due date without penalty. After the due date, that's when a penalty kicks in. Every homework assignment should also have some video description if you like, but sometimes students don't even look at it. You can go straight into this thing. So essentially what this week's homework assignment goes is I would ask you to create a solution method with two inputs. One of them is called events pushed array, and the other one is integer array, and the other one is event pops array. So imagine you're doing some editing in your Microsoft Office Word, and you write up a whole paragraph, and your Microsoft Word is keeping track of two things: everything you did and everything you undid, right? So there's this whole redo and undo features, and I'm not asking you to implement these redo and undo features, but what happens is internally Microsoft can maintain these two stacks, and your method essentially takes in these two stacks, and your job is to figure out whether they're from the same stack or not. So these are what I'm trying to do is I would produce the outcome of what this whole slew of redo and undo event is like, separate them into redo and undo, push them into the function, and your function determines whether they're from the same stack or not. So it's a little bit of playing detective, working backwards on, hey, these series of events, one of them is push and the other one is pop. They happen, in a certain way based on the events passed, from these queues, whether they're from the same stack or not, whether the application makes use of the same stack. This is coming from the same stack. If this is not from the same stack, your function or method here is going to return false. So it's either true or false, okay? And you can look at some of the examples that I gave right here, the input, the push event, and then pops event, 213, 312, are they from the same stack or not? They're not. So yeah, there's reasoning involved. So make sure you understand what the problem is, okay? And then you understand what the problem is asking you to solve before solving it. If you don't understand these examples, do not start, okay? Do not start, because then you get even more confused. So please understand how these examples work. Well, understand the problem first. Understand how these examples kind of map to the problem you're trying to solve. And understanding the problems you're trying to solve before solving it is the key to success in this class. All right. Now that you have already known the foundations of stack, how that works, try to apply solving this problem. All right. Constrain the assumption, and there's some hint you can go over if you like. Your submission should be in hw2.java, period. Nothing else. Okay. And make sure this is a .java file. Do not submit .ccpp or .c.python class files. They will not be accepted on Canvas. And only electronic submissions on Canvas will be accepted through homework submissions tab. Do not send me emails or Slack with attachments unless you want to just, comment on certain things you have questions of during office hours. You can do that, but officially your grades will be entered through work submitted on Canvas assignment only, okay, and quiz. All right, I'm going to pause right here. Any questions so far? All right, give yourself some time. This one is due on December 21st. So you have next week, the entire week. If you have questions next Saturday is where you get a chance to ask me in class, if you like. But make sure you don't get confused for indefinite amount of time. And I want to direct you in the right way. Okay. So once you get through this homework assignment number 2, every week homework assignment is going to be roughly similar. You'll be given a context, and then you'll be asked to use what you learn to solve that problem. Okay. And then there's that platform independent solution thing. And if you don't understand, that's okay. By next week or week after, you probably get more and more context like why I'm doing this. But yeah, that's it. All right. Well, it's 11 o'clock, and we can break slightly earlier if you guys want to stick out and ask questions on during the office hours, not office hour, after class on Zoom. Let me know. Otherwise, I'll lock off. Your recorded sessions will be available on Zoom in about maybe an hour or two. Otherwise, yeah, I guess we'll see you on next Saturday. I'll be on Zoom, not in person. Bear in mind, I'll send out announcements about that to remind. Otherwise, have a great weekend, folks, and see you next week. Okay. All right. Take care. Have a good one. Bye.